Hello. In the last few lectures, we have been talking about transmission line. We saw different types of transmission line like coaxial line, microstrip line and waveguides. After that, we looked into a transmission line loaded with the load impedance ZL. Then we took different cases of ZL, for example, ZL equal to 0, ZL equal to infinity, ZL equal to Z0. And then we took two special cases of length equal to lambda by 4 and lambda by 2. And we saw that when the length is lambda by 4, it acts as a quarter wave transformer. After that, we discussed about Smith chart, and we actually saw how easily we can plot complex impedance values and also how impedance matching can be done using Smith chart. So, we looked into two different techniques. One was lumped element technique and the second one was single stub matching. Today, we are going to talk about A, B, C, D and S parameters. So, no, we are not going to learn what you studied in your very low class, which is A, B, C, D, but we are actually going to look at the A, B, C, D parameters which are defined in terms of voltages and currents. And then we will talk about S parameters which are defined in terms of wave parameters, because at microwave we actually are more interested in the waves than just in voltages and currents. Then you might wonder then why we are discussing about ABCD parameters which are mainly concerned with voltages and currents. So, I am going to show you how ABCD parameters are very convenient to solve a complex network, and then we will talk about how ABCD parameters can be converted to S parameters. So, let us first look at what is the definition of the ABCD parameter. So, here we have a two port network. So, port 1, port 2, and this is a linear network, and let us see that the input voltage here at port 1 is V1 and at port 2 voltage is V2. Current is coming into the port 1 and current is also coming into the port 2. In fact, this has been a general definition. You might have studied Z parameters or Y parameters. In case of Z parameters, just to refresh your memory, what we have generally for Z parameters, V1 and V2 are on one side, I1 and I2 are on the other side, and in between there is a Z matrix Z11, Z12, Z21, Z22. In terms of Y matrix or Y parameters, we have I1, I2 on the left side and V1, V2 are on the right side, and then there is a Y matrix. In fact, there are hybrid parameters are also there which actually consist of voltages and currents, and you might have studied those hybrid parameters for transistors. Here we are going to look at ABCD parameters, and the way ABCD parameters are defined, which actually becomes easier later on as we will see to solve a complex network. So, let us see what ABCD parameters are related to. So, voltage at port 1 and current at port 1 related to voltage at port 2 and current at port 2. Now, you might see there is a minus sign over here. This minus sign is coming because we have taken this current as incoming at port 2. If we take this current I2 as outgoing, then this will become plus. So, in fact, many a times you can just think about it that if this is I2 which is coming in, just think about this is current, let us say I2 dash, and which is leaving here, then I2 dash will be nothing but minus I2, and that will be here then plus I2 dash. Okay, so, it just says matter of notation. So, how do we define ABCD parameter? Let us open the matrix first. So, V1 is nothing but A multiplied by V2, then minus B times I2, and what is I1? I1 is nothing but C multiplied by V2 minus D times I2. So, these are the ABCD parameters. Now, by using these two equations, we can find out the ABCD parameter. So, let us see what is A. We can say from here A will be equal to V1 by V2 provided I2 is equal to 0. So, if we put a boundary condition as I2 equal to 0, which is what has been put over here, then what will be A? V1 divided by V2. So, you can actually think about A is nothing but voltage ratio provided I2 is equal to 0. And at what condition I2 will be equal to 0? if this particular port is open circuit, then I2 will be equal to 0. Now, let us see how we define B. B is nothing but V1 divided by minus I2 provided V2 is equal to 0. So, if you put V2 equal to 0, so you can see here if V2 is put 0 here, then V1 divided by minus I2 will be equal to B. Now, as you can see, this is voltage divided by current. So, the unit of this will be ohm, or you can say this will represent the impedance value. Now, let us see what is C. So, to define C, you can see from this particular expression, if we put I2 equal to 0. So, what I2 equal to 0 would mean? This term will become 0. So, we can say from here C1 is nothing but I1 divided by V2 provided I2 equal to 0. So, I2 equal to 0 means open circuit, and this unit will be now I divided by V. So, that will be equal to mho. So, the unit of the C is mho. What is D? So, again from here we can find the value of D. If we make V2 equal to 0, if V2 is 0, then this term will become 0. So, then I1 divided minus I2 will be equal to D. So, you can see that this is the expression provided V2 is equal to 0, and what V2 equal to 0 would mean? That you actually short circuit the port 2. So, this is how we can actually define ABCD parameters. Now, let us just take some example and see how we can find out ABCD parameter. To start with, we will take a very simple problem, and then we will build upon these small little things to analyze a more complicated configuration. So, ABCD parameters for series impedance. So, you can see here there is basically port 1, you can say this is port 2, and there is only single element which is a series impedance. So, now for this particular case we can write the voltage equation and current equation, and you have to remember basically that we have to write V1 and I1 on one side and V2 and I2 on the other side. So, with that objective in mind, let us say what is V1. So, V1 is nothing but we can say this voltage plus voltage drop over here. So, V1 will be equal to V2 plus you can say I1Z, or I1Z is equal to minus I2Z. So, we can say that V1 is nothing but V2 minus Z times I2. So, that will be this voltage equal to this voltage drop plus this voltage over here. And what is I1? Again, why we are writing in this particular form? Because we have to write in this particular fashion. So, what is I1 equal to? I1 is nothing but equal to minus I2. So, from here you compare this particular thing with this particular equation over here. So, we can say that V1 is A V2. So, what is coefficient of V2? 1. So, that is 1 here. What is now V1 is equal to B times minus I2, and what will be B here then? Z. So, now let us see I1. I1 is nothing but C times V2. Well, there is a nothing corresponding to V2, that means C is equal to 0. And then from here we can say I1 is equal to then D times minus I2, the term. So, from here we can say compare this. So, D will be equal to nothing but 1. So, we can say that ABCD matrix for this particular case is nothing but 1 Z 0 1. Please try to remember this because we are going to use this later on. A few properties of ABCD parameter. So, one of the property is that if the network is symmetrical, then A will be equal to D. As you can see, if you look on this side or you look from this side, the network is nothing but a symmetrical network. So, A should be equal to D. You can see that A and D are 1 and 1. So, they are equal. Now, for reciprocal network, it is AD minus BC is equal to 1. Actually, this term really corresponds to the determinant of matrix ABCD. So, what will be the determinant? AD minus BC. So, the determinant of the matrix, if that is equal to 1, this is a reciprocal network. What a reciprocal network means? That if I give an input on this side, whatever the output I get, if I give this same input on this side, then I should get the same output here. So, in fact, all these networks will be reciprocal, which have, let us say, resistor, inductor, capacitor, transmission line, other thing. So, of course, if it consists of active network, then it will not be reciprocal. So, now let us take another example. So, this time we will take an example of ABCD parameters for shunt admittance. So, we have here again as before port 1 here, port 2 here. Now, instead of having a series impedance in the previous case, now we have a shunt admittance. So, now we want to write ABCD parameters of this. I have just written it again. This is how we have defined ABCD parameter. So, again we want V1 I1 on the left side. So, what is V1? This voltage is same as this voltage, which is equal to V2. So, V1 is equal to V2. And what about the current I1? So, you can say that just general you think about this current and this current. These two currents are going into this. So, we can say that I1 plus I2 will be nothing but this particular current, and that current will be nothing but V2 times Y, and then we can write I1 plus I2 was written there, I2 goes to the other side. So, now this is similar to the form which we wanted, V1 I1 on the left side, V2 I2 on the right hand side. So, again now comparison, let us say now A, B, C, D. So, you look from here. So, V1 is nothing but A V2. So, the coefficient of V2 will be 1. So, it is right here. Now, V1 is B times I2. Well, there is a no term of I2, that means B is equal to 0. For now C, let us say what is I1 is C times V2. So, C will be Y, and then I1 is this expression here, from here then I1 is CV2 minus DI2. So, you can say from here D is equal to 1. So, this is ABCD matrix for shunt admittance, which is nothing but 1 0 Y1. So, again you can say that this is symmetrical network. Why? Because A is equal to D. It is also reciprocal network because AD minus BC will be equal to 1. So, 1 into 1 is 1 minus 0. So, AD minus BC is equal to 1. Let us just take now another case of a transmission line. You might have studied about transmission line, and you know that let us say if you want to define a voltage V1, then voltage V1 is nothing but equal to V2 cos hyperbolic gamma L plus Z0 sin hyperbolic gamma L. Similarly, one can write expression for I1. Now, in this particular case here, we are assuming that this line is lossless, or we can say most of the time line losses will be very, very small. So, that cos hyperbolic gamma L, what is gamma? Gamma is alpha plus j beta. So, alpha will be negligible or alpha is equal to 0 for ideal transmission line. So, cos hyperbolic gamma L will become now cos beta L, and sin hyperbolic gamma L will become j sin beta L. So, this is what is the ABCD matrix for a transmission line. We will take one of the special case, as we will see later on when we take on more circuit examples, that this will be one of the special cases which will come several times. So, let us look at that right now. When length is equal to lambda by 4, and if you substitute L equal to lambda by 4, what will happen to beta L? So, beta is 2 pi by lambda. So, that is 2 pi by lambda. L is equal to lambda by 4, we substitute that. So, beta L becomes pi by 2. So, cos pi by 2 is equal to 0, sin pi by 2 is equal to 1, sin pi by 2 will be 1. So, we will be left with j by 0, and cos pi by 2 will be equal to 0. So, this will be the ABCD matrix for transmission line of length L equal to lambda by 4. I just want to mention a few additional thing here. Many books, instead of writing beta, they write k. So, beta is equal to k, which is equal to 2 pi by lambda. Again, one more thing I want to mention here. So, this lambda will be equal to lambda 0 in free space, but otherwise say for coaxial line, lambda will be equal to lambda 0 by square root epsilon r. For microstrip line, it will be lambda equal to lambda 0 divided by square root epsilon e. And we have given you the formulas how to calculate epsilon e for microstrip line. So, please use that when you are designing something for microstrip line. Now, let us just take another case. Now, here it is ABCD parameters for cascaded network. So, what we have here? We have two series impedances Z1 and Z1 here, and we have a one shunt admittance which is Y2. Now, this particular problem can be solved if you want to write voltage equation and current equation, you can solve that. So, you can actually write here, let us say a node equation here. So, which will be let us say some node 3. So, we can say that V3 times Y2 V plus V3 minus V1 divided by Z1 plus V3 minus V2 divided by Z1, and then you can solve the equation, or you can write a loop equation here, loop equation here. However, we are not going to use that technique. That can be done, there is no problem at all. But since we have already studied ABCD parameters for series element, we have also studied ABCD parameters for shunt element. So, now we are going to use the concept of ABCD parameters of cascaded circuit, which can be obtained by multiplying individual ABCD parameters. What it really implies? First, let us just see, we have three different circuit elements. So, what we do, if you recall, Britishers used to say divide and rule. Well, I have modified that particular statement, I say divide and solve. So, you divide this particular network into three different networks. So, this will be from here to here, one network which consists of only series impedance, then from here to here it will be the shunt admittance network, and then from here to here we will have a series impedance network. So, what is this cascaded business? So, let us just see from here. Just recall, now we had taken I1 as here, and just imagine that the current was entering here. Now, the current which was entering here, which was minus, but that minus current can be think about positive current over here, and then the current which is leaving here, which was actually minus, which will act as a entering here. So, if you look at just this particular network, so V1 I1 for this, let us say I did mention a V3 node here. So, that will be V3 node over here. So, we can actually say that ABCD parameter of this, whatever is the current going out from here will become input current and input voltages over here. So, that means this ABCD matrix can be multiplied with this, and then again whatever is the current coming in, the same current is going, just the directions are different. So, you have to take care of that part, which is inherent of ABCD matrix. So, what we can do actually, that to find out the overall ABCD matrix, what we simply need to do it is multiply ABCD matrices of these three separate elements. So, let us see, for the series impedance, what we had seen, ABCD parameters are 1, Z1, 0, 1. For shunt, we had 1, 0, Y2, 1. For series, it is 1, Z1, 0, 1. So, now all you have to do it is multiply these three matrices. Of course, you do one by one. So, first you multiply this matrix with this matrix here, and then after that this resultant matrix is to be multiplied by this matrix here. So, just one step in between, you simplify, this is the expression you will get. And just to see whether you have done any mistake or not, you can make a quick check whether the network is symmetrical and reciprocal or not. You can see from here, if we look from this side or we look from this side, network is symmetrical from both the sides. So, hence A should be equal to D. Let us see whether we have got that or not. So, this is 1 plus Z1 Y2, this is 1 plus Z1 Y2. So, we can say A is equal to D. Now, this network is reciprocal because all these are nothing but RLC component. So, that is reciprocal network. So, let us see AD minus BC is equal to 1 or not. So, now you multiply this with this here, what we will get? 1 plus 2 times Z1 Y2 plus Z1 square Y2 square. Now minus this term here, 2 Z1 Y2. So you can say that 2 Z1 Y2 will get cancelled by these two terms combined together, and this is now Z1 square Y2 square. So we had also got Z1 square Y2 square. So subtraction from here to here will lead to a value which is equal to 1. So that means this is a reciprocal network, and that really means that so far we have done the correct calculations. Now we are going to take many more examples later on about ABCD parameters, especially just to mention that I did take an example of transmission line. So we will see many cases later on where this particular component may be a transmission line, or this component may be a transmission line, or there may be some lumped element. So you have to wait for few more lectures, and then we are going to take several examples where we are going to use these properties of ABCD parameters, and especially we will use the concept of divide and solve the problem. Now we are going to the next particular topic, which is S parameters. Here we have defined S parameters for 2-port network, but by the way S parameters are valid for N-port network also. Just to tell you that ABCD parameters are defined only for 2 ports, but S parameters are defined for N port. But for simplicity, let us just take 2 port and then we will extend this concept to N ports. So let us see what we have here. So here A1 is the incoming wave. So it is not same as current, it is an incoming wave, and B1 is reflected wave. So we are talking about now microwave frequency, where we do not talk about voltages and currents, whereas there we call, let us say, an antenna which will receive the signal, and through the antenna we can transmit the signal. So there are incoming waves or outgoing waves. Similarly for an amplifier, there will be incoming wave, there will be outgoing wave. So generally speaking, when we deal with S parameters, they are dealing with waves. So A1 is incoming wave, similarly A2 is incoming. So A parameters are incoming. So over here B1 is outgoing, sometimes they say, or leaving wave. So this is the outgoing wave or leaving wave. Okay. Sometimes in some books they also talk this as a transmitted wave also. Okay. Or over here they use the term reflected wave. So in this case, if this is incident, this is, you can say, reflected, and if this is incident, this can be transmitted wave. Okay. So it all depends how you look at it, but basically we just say that A1 or all A's are incident wave, all B's are reflected wave. Now we will define the S parameters. So we can actually define B1, B2 on this side, that means these are the reflected wave, these are the incident wave, and this is how we defined S parameters. Okay. We can open the matrix. Let us look at here. So B1 is equal to S11 A1 plus S12 A2. We can write B2 as S21 A1 plus S22 A2. So now from here, just as we did in terms of ABCD parameter, we will just exactly the similar thing. So let us say from here, how we can find the value of S11? So we can find S11 by making, let us say, A2 equal to 0. So if A2 is equal to 0, then S11 will be given by B1 divided by A1. So you can see that S11 is nothing but B1 divided by A1, provided A2 is equal to 0. Now here, unlike the previous case where voltage equal to 0 implied short circuit, current equal to 0 implied open circuit, here A2 equal to 0 implies match load termination. If you recall, when we had mentioned about it, that if something is going from here and over here, so nothing should reflect back, and if nothing will reflect back only when it is terminated into a matched load. Okay. And here we are defining everything in terms of characteristic impedance Z0. So if this particular port is terminated with the characteristic impedance of Z0, that means load is equal to Z0, in that case nothing will reflect. So A2 will be equal to 0. So please remember, when we define S parameters, we are not dealing with short circuit or open circuit, we are more dealing with the match load termination. So, now let us see from here how we define S12. So, S12 will be equal to B1 divided by A2 provided A1 is equal to 0. So, you can see that S12 is nothing but B1 divided by A2 when A1 is equal to 0. So, what A1 equal to 0 really means? That means now port 1 is terminated into match load, and what it really means here. So, this means that when we are giving input at port 2, what is the output at port 1 or what is the wave going out here. Now, let us see what is S21. S21 is nothing but B2 divided by A1 provided A2 is equal to 0, and similarly we can find out S22. What is S22? S22 is nothing but B2 divided by A2 provided A1 is equal to 0. So, please remember these things. So, S11 actually can also be termed in a slightly different way, that is, look at the port 1 here, this is S11. What is B1? Reflected wave. What is A1? Incident wave. So, what we are basically saying, S11 is nothing but reflected wave at port 1 divided by incident wave at port 1. Let us see what is S22. S22, we have to look at the port 2 here. What it shows here? This is the incident wave, this is the reflected wave provided this is terminated with the match load to get A1 equal to 0. So, that means S22 is nothing but a reflected wave which is B2 divided by A2. So, this is same thing as reflection coefficient at port 2, this is the same thing as reflection coefficient at port 1. Now, let us see what is S21. S21 is defined as B2 by A1. What is B2? Wave going over here. What is A1? Incident wave over here provided A2 is equal to 0. So, that means if we terminate this thing into a match load, then what is the transmitted wave to this particular value divided by the incident. So, hence this you can say will actually give the gain of the amplifier or loss of any given circuit. So, that is why many a times B2 is mentioned as transmitted wave when A1 is the input here. Okay, but if you look at S12, what is S12? That is B1 divided by A2 provided A1 is equal to 0. So, that means if input is given at port 2 which is A2, then what is the wave going towards this? So, in this particular case, if the input is at port 2, then B1 becomes transmitted wave. So, B1 divided by A2. Okay. So, in the next lecture, we are going to talk in more detail about S parameters, how these reflection coefficients and transmission coefficients are defined. So, just to summarize today's lecture, so we actually started with the very simple ABCD parameters which are defined in terms of input voltages and current and output voltages and current. And the benefit of that is that for one network, if this input voltage and current is defined in terms of output voltage and current, then that output voltage current becomes input voltage and current for the next port, and then we can find the next to next port output voltages and current. So, you can keep cascading these things, and simply by multiplying ABCD of first to second to third or fourth or n different components can be there, and you can find ABCD parameters of the entire network simply by doing the matrix multiplication. And then we did look at a few simple examples. One was series impedance, then another one was shunt impedance, then we looked at the transmission line, and then we also looked at one case which consisted of series, shunt, series. Okay. And after ABCD parameters, we looked at S parameters. Now, ABCD parameters are defined in terms of voltages and currents. S parameters are defined in terms of incoming wave and outgoing wave. And in the next lecture, we will see that how ABCD parameters are related with S parameters, how we can convert from ABCD parameters to S parameters, and also we will look at what are the different properties of S parameters and what happens when you go from 2 port to n ports. So, what are the different things? We will look into that, and we will also see how to calculate S parameter for a given network. So, with that, thank you very much. See you next time. Bye.